Okay, so let's go through the solution to chapter 14, problem 57. Let's quickly read through the problem. We have two pendulums, each consisting of a solid ball of mass m supported by a rigid massless rod. Okay, but the ball for pendulum A is very tiny, so we have just a little ball here for pendulum A, where the ball for pendulum B is a really large ball. Okay, find the period of each pendulum for small displacements. Which ball takes longer to complete a swing? All right, so this problem doesn't have any numbers, right? So this is a problem where we're going to use equations and solve symbolically, using symbols, of course. And secondly, it's kind of an interesting conceptual exercise because we have two pendulums. They both have exactly the same mass, right? They both have a mass of m, and the distance between the center of mass for this ball, the center of mass is right there, and the ceiling. So the distance of the length of the pendulum is equal to L. And for this ball, the center of mass is right here, right? That's the center of mass. So the distance between the center of mass and the ceiling, in this case, the length of a pendulum, is also L. So we have two pendulums with exactly the same lengths and exactly the same mass. And the question is, do they have the same period? Okay, so for pendulum A, we can recognize, just conceptually, this is what is called a simple pendulum. Right? All of the mass is at exactly the same distance from the axis of rotation. Right? The pendulum is oscillating about this point here. It's oscillating in some, circular motion here. All of the mass is basically at the same distance. So that's what we call a simple pendulum. For mass B, this is not a simple pendulum. Right? Some of the mass is really close to the axis of rotation, while some of the mass is much farther away. Right? So as this object moves in kind of this circular path, this mass out here is going a lot farther in the same amount of time, so this mass is moving faster, has more kinetic energy, where this mass here is going smaller in the same amount of time, a smaller distance in the same amount of time. This part of the mass of the ball has a smaller kinetic energy. So this leads us to believe we should probably be using moment of inertia to figure out the period of this pendulum. This is a physical pendulum, this is a simple pendulum. Okay, so for a simple pendulum, we have a nice simple formula for that. The period of oscillation for a simple pendulum, in this case, pendulum A, is just given by, this is on your equation sheet, 2 pi square root of L over G. All right, so that's all we need to do to figure out the period of this pendulum, is just recognize this is the relevant equation. We know L, we know G, it's the acceleration due to gravity. And so just knowing those two things, I know the period of this pendulum, right? It doesn't depend on the mass of the pendulum at all, okay? And I can use this equation, again, because all the mass is at the same distance from the axis of rotation. Okay, for ball B, as we noted, we can't use this formula because some of the mass is further away, some of the mass is closer, so we have a distribution of mass. This is a physical pendulum. We're going to need to use the equation for a physical pendulum. And so that equation, again, on your equation sheet, is 2 pi times the moment of inertia divided by the mass times the acceleration due to gravity times d, where d is the distance between the center of mass and the axis of rotation. Okay, so we know that value. So in order to use this formula and figure out the period, I need to figure out the moment of inertia. Right? So this sphere, again, it's a sphere. I can look up the moment of inertia of a sphere, but it's not oscillating about its center of mass, right? It's oscillating about this point up here, a distance L from the center of mass. So to figure out the moment of inertia, I'm going to have to use the parallel axis theorem, right? I can look up the equation for the moment of inertia of a sphere rotating about its center of mass, and then I can pick a parallel axis right here and figure out the moment of inertia about that axis. Okay, so let's try to figure out the moment of inertia. The moment of inertia of a sphere is equal to 2/5 mr squared. That's for a solid sphere. Okay, and in this case, what is the radius of the sphere? Well, I can see that this distance is L over 2, and this distance is L, so it must be that the radius, or this distance, is also L over 2. All right, so the moment of inertia of the sphere about a center of mass would be 2/5 times the mass times L over 2 squared. Okay, So I have 2 over 5 times 4, or 2 over 20, or 1/10 ml squared. All right, so that's the moment of inertia of that sphere about its center of mass. Let me be clear there, about the center of mass. We are not oscillating about the center of mass. So I'm going to bring into play here our parallel axis theorem. The moment of inertia about a parallel axis is equal to the moment of inertia about the center of mass plus the mass of the object, which is moving in a circle, or in this case oscillating back and forth, times the distance between the center of mass and the parallel axis squared. Okay, and so I have the moment of inertia of the center of mass is equal to 1/10 ml squared. That's what I figured out in the previous part, plus mass times d, where d again is the distance between the center of mass and the axis of rotation, and that distance is L. Okay, so plus ml squared. So I find that the moment inertia of the sphere about this parallel axis is 1/10 plus 1, or 11/10 ml squared. Okay, so you can note here that the moment inertia of the sphere about the axis it's rotating about is much, much larger than the moment inertia about its center of mass. Okay, it's going a lot. There's a lot of mass at a far distance from the axis of rotation, traveling really far. This thing has a lot of kinetic energy as it's moving. Okay, that's one conceptual way of thinking about that. So, okay, we know the moment inertia about the parallel axis now. So now I have what I need to plug into this equation. Okay, let's do that here. So to figure out the period of this physical pendulum, I again use the formula 2 pi square root of I over mgd. I figured out that the moment of inertia is equal to 11/10 times ml squared. Okay, and in the denominator I have m, I have g, and again d here is the distance between the center of mass and the point we're oscillating about. And so that distance is, again, for this pendulum, what they told us was L. Okay, so I have just mgl in my denominator here. Okay, so I need to solve this symbolically so that I can compare this period to the one for the simple pendulum. So let's try to do that. Our mass cancels, one term of L cancels, so I have 2 pi times the square root of 11 over 10 times the square root of L over G. So let's write that again, and I'm just going to rearrange in a little bit of a different way. I'm going to bring out the square root of 11 over 10, and then I have 2 pi times the square root of L over G. Okay, and I note that this part is just our equation for the period of pendulum A. Right, that's what we found up here, 2 pi times the square root. Okay, so what we found is that the period for pendulum B is now the square root of 11 over 10 times the period for pendulum A. Okay, this number is definitely one that's bigger than 1. In fact, if you plug that into a calculator, you find this is about 1.05 times the period for pendulum A. Okay, so what we found is that, let's get back to our picture here. For pendulum A, we'll just call the period T sub A. The period for pendulum B is 1.05 times the period for pendulum A. So this period must be longer than this period. Right? So this pendulum, even though it has exactly the same mass and exactly the same length as this pendulum, has a larger period. It takes longer to go through one complete cycle, one complete oscillation. Okay? And so that demonstrates the importance of the moment of inertia, the fact that for pendulum B, the mass is distributed over a large area. Some of the mass is located really far away from the axis of rotation, and therefore as it moves, it's traveling a further distance, therefore it must be moving faster, and therefore it has more kinetic energy. Okay, and that has the effect of changing the period of this pendulum. Okay, so mass distribution matters.